The experiment that shattered reality. A question you cannot unask. Close your eyes for a moment. I want you to imagine something. You are standing in a dark room. There is a wall in front of you with two thin slits carved into it. Behind that wall is a blank screen. Now imagine you pick up a handful of tiny marbles and throw them, one by one, toward that wall. Some go through the left slit, some go through the right. They hit the screen behind the wall and leave little marks, two clusters, two stripes. Simple, predictable, the kind of thing a child could understand. Now open your eyes, because I am about to tell you something that will change the way you see everything around you. When scientists did this exact experiment, not with marbles, but with particles, the smallest building blocks of everything you see, touch, and feel, the result was not two stripes. It was impossible. It was as if the particles knew something they had no right to know. It was as if they were watching themselves. And when the scientists tried to watch too, to catch the particles in the act, the particles changed their behavior. They stopped doing the impossible thing. They went back to making two simple stripes, as if they knew they were being observed. This is not a thought experiment. This is not a metaphor. This is real. It has been confirmed thousands of times in laboratories around the world for over 100 years. And no one, not a single physicist alive, can fully explain why it happens. This is the double slit experiment. Richard Feynman, one of the greatest minds of the 20th century, once said that this single experiment contains the only mystery of quantum mechanics. He said that if you think you understand quantum mechanics, you do not understand quantum mechanics. And tonight, I am going to walk you through this experiment so completely, so carefully, that by the end of this video, you will understand exactly why the greatest scientific minds in history lost sleep over two tiny slits in a wall. Welcome to the Conscious Observer. My name is your guide, and this is the experiment that shattered reality. The world before the cracks. To understand why the double slit experiment is so devastating, you first have to understand the world it destroyed. Rewind to the late 1800s, the age of certainty. Physics was considered essentially finished. Lord Kelvin, one of the most respected scientists of that era, reportedly declared that there was nothing new to be discovered in physics and that all that remained was more and more precise measurement. Imagine the arrogance. Imagine the confidence. The universe, according to the scientists of that age, was a giant clockwork machine. If you knew the position and velocity of every particle in the universe at any given moment, you could, in theory, predict the entire future. Every sunrise, every raindrop, every human thought. It was all just billiard balls bouncing off one another in predictable patterns. Isaac Newton had given us the laws of motion. James Clerk Maxwell had unified electricity and magnetism. Thermodynamics explained heat and energy. The great puzzle of nature seemed to be solved, and all that was left was to fill in the decimal places. But there were cracks, small ones, annoying little problems that refused to go away. There was the mystery of blackbody radiation, the strange way heated objects emitted light that did not match the predictions. There was the photoelectric effect, where light hitting metal released electrons in ways that classical physics could not explain. These were treated as footnotes, minor irritations. Nobody realized they were not cracks in the wall. They were cracks in reality itself. And the experiment that would blow those cracks wide open, the experiment that would bring the entire edifice of classical certainty crashing down, involved nothing more than a beam of light, a barrier with two slits and a screen. That is all it took to shatter a worldview that had stood for 3 centuries. Two slits. Let me show you how. The experiment. What should happen versus what actually happens. Let us build this experiment together, piece by piece, the way a physicist would. First, take a flat barrier, cut two narrow parallel slits into it, close together. Place a detection screen behind the barrier, something that records where particles land. Now, get yourself a particle gun, something that fires tiny objects, one at a time, toward the barrier. If we use actual bullets, actual physical things like tiny ball bearings, the result is exactly what you would expect. Some bullets go through the left slit, some go through the right slit. On the detection screen, you get two bands of impact marks, one behind each slit. This is called a clump pattern. It is boring. It is predictable. It is classical physics working exactly as advertised. Now, let us switch to waves. Instead of bullets, let us send water waves toward the barrier. Something different happens. When a wave hits the barrier, it passes through both slits simultaneously. On the other side, Two new waves emerge, one from each slit, and they spread outward. Where the peak of one wave meets the peak of the other, they combine and create a bigger wave. Where the peak of one meets the trough of the other, they cancel each other out. This creates what is called an interference pattern on the screen behind the barrier, a beautiful series of alternating bright and dark bands. Bright where the waves reinforced each other, dark where they canceled. This is the signature of waves. Only waves do this. Particles do not. Particles cannot. This distinction between particle behavior and wave behavior was crystal clear for centuries. Particles make clumps. Waves make interference patterns. They are fundamentally different phenomena. And that is why, when scientists began firing electrons, tiny subatomic particles, through the double slit, they expected to see two clumps, one behind each slit, just like the bullets. But that is not what they saw. What they saw was an interference pattern. The signature of waves. Electrons, tiny discrete particles of matter, were behaving like waves. And that, right there, is where the universe started whispering secrets it was not supposed to tell. The deepening mystery. One particle at a time. Now, you might be thinking, well, okay, maybe the electrons are bumping into each other. Maybe when you fire a bunch of them at once, they interact, they interfere with one another, and that is what creates the wave pattern. It is a reasonable thought. It was the first thought many physicists had too. So they decided to test it. They turned down the electron gun to its absolute minimum, one electron at a time. Fire one. Wait. Fire another. Wait. Each electron is completely alone. There is no other electron to interact with, to bump into, to interfere with. Each one travels through the apparatus in total isolation. And when they hit the screen, each one lands as a single dot, a tiny, definite point of impact. Exactly what a particle should do. So far, so good. But then the scientists did something that changed everything. They waited. They let the dots accumulate. 10 dots, 100 dots, 1,000, 10,000. And slowly, dot by dot, like a photograph developing in a darkroom, a pattern began to emerge. An interference pattern. The wave pattern. The same pattern that only waves are supposed to make. But there was only one electron at a time. There was nothing for it to interfere with. No other particle, no other wave. It was alone. So how do you get a wave interference pattern from individual particles that are traveling one at a time? The only mathematical explanation, the one that the equations demanded, was that each individual electron was somehow passing through both slits simultaneously, a single particle, in two places at once, not metaphorically, mathematically. The electron, when it was not being observed, was not a particle at all. It was a wave of probability, a cloud of potential, spread out across space, passing through both slits, interfering with itself, and only becoming a definite particle when it hit the screen. Let that sink in. A single object, passing through two separate openings at the same time. This is not science fiction. This is the foundation of modern physics. And we are not even at the strange part yet. The observer effect. Reality watches back. Here is where the story takes a turn that sounds like it belongs in a horror film. The physicists were understandably disturbed. Electrons going through both slits at once? That cannot be right. So they decided to look. They placed a tiny detector at the slits, something that could record which slit each electron actually passed through. Left slit or right slit. Just a simple measurement. They were not changing anything about the experiment. Same electron gun, same barrier, same slits, same screen. The only difference was that now they were watching, and the interference pattern vanished. Gone. Completely. The moment the scientists observed which slit the electron went through, the electron stopped behaving like a wave. It went through one slit or the other, never both. And on the screen, instead of the beautiful interference pattern, there were just two clumps. The boring, predictable, classical result. As if the electron knew it was being watched. Turn the detector off. The interference pattern returns. Turn it on. Two clumps. Off. Wave pattern. On. Particle pattern. Over and over again. Without fail. Let me be very precise about what is happening here because it sounds insane and it is easy to dismiss as an exaggeration. The electron is not being pushed by the detector. The detector is not physically interfering with the electron's path in any meaningful way. It is simply gathering information. It is simply observing. And that observation, that mere act of looking, changes the physical outcome of the experiment. The act of measurement transforms wave behavior into particle behavior. The act of knowing which path the electron took forces the electron to have taken only one path. The universe, it seems, behaves differently when someone is looking. And that is not a philosophical statement. It is an experimental fact, replicated, confirmed, undeniable. The question it raises is terrifying. If observation changes reality, then what is reality when nobody is watching? Going deeper, delayed choice, and the rewriting of history. If you thought the observer effect was strange, hold on. Because John Archibald Wheeler, one of the titans of 20th century physics, the man who coined the term black hole, decided to push this experiment to its absolute breaking point. Wheeler proposed what he called the delayed choice experiment. The idea is diabolically simple. What if you do not decide whether to observe the electron until after it has already passed through the slits? Think about that. The electron approaches the barrier. It must decide, so to speak, whether to go through one slit or both. If nobody is watching, it goes through both and creates an interference pattern. If someone is watching, it goes through one. But what if you make the decision to watch or not watch after the electron has already passed through the barrier? It is too late. The electron already made its choice. It already went through one slit or both. The decision is in the past, except it is not. When this experiment was actually performed, and it has been performed many times, the results defied everything we think we know about time and causality. If the scientists chose to observe after the electron had already passed the slits, the electron behaved as a particle. One slit. No interference. If they chose not to observe, even though this choice came after the electron had already passed, the electron behaved as a wave. Both slits. Interference pattern. The observation was not just changing the present, it was reaching back in time and changing the past. The electron's history, its trajectory, whether it went through one slit or two, was not determined until it was measured, even if the measurement came after the event had already occurred. The past was not fixed. The past was waiting to be defined by a future observation. Wheeler himself said it best. He said that no phenomenon is a real phenomenon until it is an observed phenomenon. The universe, it appears, does not just respond to observation. It retires its history, edits its own story, based on whether and when someone decides to look. I want you to sit with that for a moment. Your intuitive sense of time, the feeling that the past is solid, fixed, done, is wrong. At the quantum level, the past is as fluid as the future, and it takes an observer to pin it down. This is not mysticism, this is physics. And it gets stranger still. The quantum eraser, unknowing what you know. Scientists, as you might imagine, were not satisfied with merely breaking time. They wanted to push further. So they created what is called the quantum eraser experiment. And what it reveals will make you question whether reality has any fixed nature at all. Here is the setup. Fire electrons through the double slit, but this time, mark them. Tag each electron so you can tell which slit it went through. When you do this, as we have already discussed, the interference pattern disappears. The electrons behave as particles, two clumps. But now, here is the twist. After the electrons have been marked, after they have already landed on the screen, erase the information. Destroy the record of which slit each electron went through. And what happens? The interference pattern comes back, not in a new run of the experiment, in the very same data, among the electrons that already landed. When you look at only the electrons whose path information was erased, they show a wave interference pattern. The ones whose path information was preserved show a particle pattern. The same electrons in the same experiment simultaneously demonstrate both behaviors depending on whether the information about their path still exists. It is not the observation itself that collapses the wave function. It is the existence of the information. If the information exists, anywhere, in any form, reality is particle-like. If the information is erased, reality reverts to wave-like behavior, even retroactively. There is a version of this experiment called the delayed choice quantum eraser, first performed by Yoon-Ho Kim and colleagues in 1999, where the decision to erase or preserve the information is made after the electron has already been detected on the screen. And the result holds. Erasing future knowledge changes past behavior. This is not a loophole. This is not a trick. This is the universe telling us something fundamental about the nature of information, observation, and reality. And what it is telling us is that reality is not made of stuff, it is made of information. And the rules governing that information are nothing like what we experience in our everyday lives. Interpretations. What does it all mean? So we have established the experimental facts. Particles behave as waves when unobserved. Observation collapses them into definite states. The past is not fixed. Information shapes reality. These are not theories, these are results. But what do they mean? This is where physics ends and philosophy begins, and the debate that has raged for nearly a century shows no signs of resolution. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, remains the most widely taught. It says, essentially, do not ask. The wave function is a mathematical tool for predicting probabilities. When you measure, you get a result. What happens between measurements is not a meaningful question. The electron does not have a definite state until it is observed, and asking what it was doing before observation is like asking what is north of the North Pole. The question itself is malformed. Then there is the many worlds interpretation, proposed by Hugh Everett in 1957. Everett said, the wave function never collapses. Instead, every possible outcome of every quantum event occurs, but in separate, branching universes. When the electron reaches the double slit, the universe splits. In one branch, it went left. In another, it went right. In yet another, it went through both. All outcomes are real. You simply find yourself in one branch, unaware of the others. The cost of this interpretation is staggering, an infinite, ever-branching tree of parallel realities. But it has the elegance of requiring no special role for measurement and no mysterious collapse. And then there is the consciousness interpretation, championed by Eugene Wigger and, in different forms, by John von Neumann. This view says that consciousness itself is what collapses the wave function. A detector alone is not enough. An unconscious measuring device simply becomes entangled with the particle in a larger superposition. Only when a conscious mind becomes aware of the result does the wave function collapse into a definite outcome. In this view, consciousness is not a byproduct of physics. It is a fundamental ingredient of reality. The universe needs minds to become real. Each of these interpretations is consistent with the experimental data. None of them can be proven or disproven by current experiments. And each one leads to a radically different picture of what reality is. You get to choose which one disturbs you the least. But make no mistake, they are all disturbing. The participatory universe. You are not a spectator. Let me take you back to John Archibald Wheeler one more time, because what he proposed near the end of his life may be the most profound idea in all of science. Wheeler spent decades thinking about the double-slit experiment and its implications. He was there at the birth of quantum mechanics. He worked with Niels Bohr. He mentored Richard Feynman. He saw the entire arc of 20th century physics unfold. And at the end of it all, he came to a startling conclusion. He said that we live in a participatory universe, not a universe of things, not a universe of objects existing independently of anyone looking at them, a universe that requires participation to exist. Think about what that means. Classical physics painted a picture of a cosmos that would carry on perfectly well without a single conscious being in it. Stars would burn, planets would orbit, atoms would vibrate. The universe was a machine, and consciousness was just an accidental passenger. Wheeler said no. He said the universe is not a thing, it is a process, and observation is part of that process. Without observers, without participation, the universe exists only as a fog of possibilities. No definite outcomes, no actual events, just a shimmering cloud of potential waiting to be made real by the act of observation. He drew a famous diagram, a U-shaped figure with an eye at one end, representing the universe looking back at itself through conscious beings. The universe creates observers. Observers, through their participation, create the universe. It is a self-exciting circuit, Wheeler called it, a strange loop of existence in which the observer and the observed are inseparable. This is not poetry, though it sounds like it. This is a theoretical framework motivated by decades of experimental results. The double-slit experiment is its foundation. The delayed choice experiment is its confirmation. The quantum eraser is its exclamation point. You are not a spectator in this universe. You are a participant. Every measurement you make, every observation, Every act of attention is part of the process by which reality comes into being. That is not a motivational slogan. That is the implication of our best physics. And if it is true, it changes everything about how we understand ourselves and our place in the cosmos. The invitation, what comes next? So where does this leave us? We started with two slits in a wall and a handful of tiny particles. And from that impossibly simple beginning, we have arrived at the edge of everything. We have seen that particles are not really particles. They are clouds of possibility that only become definite when observed. We have seen that the act of observation does not passively record reality, but actively shapes it. We have seen that the past is not fixed, that the history of a particle can be rewritten by a future choice. We have seen that information itself, not matter, not energy, but information may be the most fundamental thing in the universe. And we have encountered the possibility, taken seriously by some of the greatest minds in physics, that consciousness is not a side effect of a material universe, but a necessary ingredient in the recipe of reality. All from two slits. All from asking what happens when you fire a particle at a wall. This is why Richard Feynman said this experiment contains the only mystery. Because every mystery of quantum mechanics, superposition, entanglement, wave function collapse, the measurement problem, the nature of reality itself, all of it is already here, hidden in this simple setup. We have not solved it. Nobody has. It remains one of the deepest open questions in all of science. But we have looked at it honestly. We have followed the evidence where it leads, even when it leads to places that make us uncomfortable. And that is what the conscious observer is about. Following the evidence, asking the questions that matter, not flinching when the answers are strange. In the next episode, we will go deeper. We will ask whether consciousness itself is the ground of reality. We will explore the hard problem of consciousness, the mystery of subjective experience, and the startling possibility that mind is not produced by matter, but that matter is produced by mind. But for now, I want to leave you with one thought. The double slit experiment has been telling us something for over a century. It has been whispering to every generation of physicists who dared to listen. And what it whispers is this: the universe is not what you think it is. It is stranger, it is more beautiful, it is more deeply connected to you than you have ever imagined. And it is waiting, right now, for you to observe it. So keep watching, keep questioning, keep observing, because in a universe where observation shapes reality, what you pay attention to is not just important, it is everything. I will see you in the next one.